you ever wondered where that missing sock goes when it vanishes from the laundry? No trace, no explanation, just gone. Or why time seems to crawl when you're bored, but flies when you're having fun. These little mysteries pepper our daily lives, nudging at something deeper we can't quite put our fingers on. We shrug them off, laugh at them, maybe blame the dog. But what if the universe plays by stranger rules than we ever imagined? What if the everyday oddities we take for granted hint at something far more profound, invisible rips in reality? Doorways to places we can't see, or maybe even shortcuts through the cosmos. Out there in the vast darkness of space, astronomers have discovered monsters that devour light itself. Black holes, the ultimate cosmic traps. And not far from them in theory, lie wormholes. Tunnels that could just maybe link one corner of the universe to another in the blink of an eye. These aren't just sci-fi fantasies. They're grounded in real physics, whispered about in equations and glimpsed in simulations. Black holes warp time and space like a bowling ball warps a trampoline, bending reality around them. Wormholes, they're the what if that scientists are still chasing, a possibility born from Einstein's own equations. So what does all this have to do with us? The people losing socks, running late, and watching time slip away. Maybe everything, because if black holes can bend time and wormholes can bridge unimaginable distances, then we have to ask, what if the universe is hiding secret passageways? And we've already passed through one without even knowing it. Imagine the universe as a giant, stretchy fabric, like a smooth rubber bedsheet stretched out in every direction. This fabric is called space-time, and it's the stage where everything in the cosmos plays out. Stars shine, planets orbit, galaxies swirl, and even time itself flows across this sheet. Now, drop a bowling ball onto the center of that sheet. What happens? It sags. The heavier the ball, the deeper the dip it makes. That's how Einstein's theory of general relativity explains gravity. Massive objects like the Earth or the Sun don't pull things toward them the way magnets do. Instead, they bend the space-time fabric around them, and smaller objects like satellites or moons roll along those curves. It's not a mysterious force pulling you down. It's just the shape of space telling you where to move. Gravity, in essence, is geometry. Now, imagine if you pressed your finger into that rubber sheet hard enough to poke a hole. Or better yet, what if something could stretch the sheet so much that it didn't just sag, but actually connected to another part of the sheet altogether? That's the idea behind a wormhole, a sort of tunnel or shortcut between two distant points in spacetime. To really understand this, let's bring in black holes. Black holes form when massive stars collapse under their own gravity, squeezing matter into a point so dense that even light can't escape. Picture a trapdoor in the bedsheet. Once something falls in, it's gone. The more mass you cram into one point, the deeper and steeper the curve in spacetime becomes, until it punches through. Black holes are like the extreme version of gravity. Instead of just creating a shallow dip in the fabric, they make a bottomless pit. But here's where it gets interesting. According to Einstein's equations, under just the right conditions, you might not end up with a one-way trapdoor. Instead, you could get a tunnel, a bridge from one place in spacetime to another. This theoretical bridge is called an Einstein-Rosen bridge, what we commonly refer to as a wormhole. Let's go back to our fabric analogy, but add a twist. Picture two dots on opposite ends of the sheet. Normally, to get from one to the other, you'd have to travel across the surface, a long journey. But what if you folded the sheet so that the two dots touched and then punched a hole through? Suddenly, you're not traveling across the sheet at all. You're going straight through it. That's what a wormhole does. It bends spacetime in such a way that two faraway places are suddenly right next to each other. The universe's own shortcut. Black holes and wormholes are like two sides of the same coin. One traps everything, including light. The other offers a possible escape, or at least a shortcut, through the universe. Both arise from the same basic rule: mass and energy bend spacetime. Whether that bend leads to a one-way plunge into darkness or a tunnel across the stars depends on the circumstances. It's all part of the strange, beautiful logic of the cosmos. A place where space can fold, time can twist, and the farthest stars might be just a tunnel away. So next time you look up at the night sky, ask yourself, what if that star isn't just far away, but actually right next to us, separated only by a hidden doorway in space? And here's the mind-bending question to leave you with. If wormholes can connect 2 points in space and time, is it possible that one is hiding near us and we just haven't noticed it yet? In the spring of 1935, 2 men sat hunched over scribbled equations and chalkboards in Princeton, chasing an idea that would stretch the imagination of physics beyond the visible universe. Albert Einstein, already a legend, and his younger collaborator Nathan Rosen were attempting to solve one of the thorniest puzzles in general relativity. They weren't trying to invent sci-fi portals or cosmic tunnels. Instead, they were hunting for mathematical beauty, a way to avoid the ugly singularities predicted by black holes, those infinitely dense points where physics breaks down. What they found instead was something that would later ignite science fiction and steer generations of scientists a bridge hidden within the fabric of spacetime itself. The idea was elegant and strange. In their now famous paper, Einstein and Rosen discovered that the equations of general relativity allowed for 2 separate sheets of space connected by a throat, a tunnel that curved through higher dimensional space. It looked on paper like a kind of worm tunneling through an apple, linking one surface to another without crossing the skin. Today, we call this construct an Einstein-Rosen bridge. At the time, they were just trying to make sense of black holes and how particles might behave in such warped terrain. But they accidentally cracked open the doorway to something far more bizarre, the possibility that the universe might be connected in hidden ways where shortcuts through space, and even time, could theoretically exist. Einstein himself wasn't comfortable with the implications. He disliked the notion of black holes as physical objects, preferring a universe that was tidy and continuous. He didn't live to see just how wild his own math would become. But the Einstein-Rosen bridge lay dormant for decades, a curious mathematical artifact waiting for someone to ask, what if this thing is real? Fast forward to the 1980s. Enter Kip Thorne, a theoretical physicist at Caltech and a leading expert on the warping of spacetime. Thorne wasn't interested in writing science fiction, but science fiction had come knocking. His friend, physicist turned author Carl Sagan, was working on a novel that would become Contact and needed a scientifically accurate way for his characters to travel across the galaxy in a human lifetime. Sagan asked, could a wormhole do the trick? That question lit a fire in Thorne. Along with his students, he dove into Einstein's equations again, this time not to dismiss the wormhole, but to test its limits. Could one be traversable? Could something pass through it without being crushed or destroyed? What they found was mind-blowing. The math said, yes, but only if the wormhole's throat was propped open by a special kind of material, exotic matter, with negative energy density. This was no ordinary substance. It violated all our usual intuitions about how matter behaves, yet quantum physics suggested it might actually exist in small amounts. Thorne's papers, especially one co-with authored Michael Morris and Ulvi Yurtsever in 1988, gave the first serious scientific framework for traversable wormholes. It was no longer just a quirky solution buried in Einstein's work. It was a blueprint, however speculative, for interstellar travel. More than that, they found that wormholes weren't just spatial shortcuts. Because spacetime is unified, bending space can also bend time. With enough clever engineering, rotating one end of the wormhole, accelerating it, manipulating gravity, you might even create a time machine. Naturally, that raised eyebrows. Time travel brings with it all the paradoxes and mind benders you can imagine. What if you go back and stop your own birth? What happens when cause and effect get scrambled? Thorne took these questions seriously and even worked out ways to preserve consistency, such as the idea that the universe somehow protects itself from paradoxes. Around the same time, another towering figure stepped into the aeronaut, Stephen Hawking. Hawking was fascinated by black holes and famously proposed that they weren't entirely black. In 1974, he showed that quantum effects would cause black holes to emit radiation, now called Hawking radiation, slowly evaporating over time. This stunned the scientific world and opened a new frontier between gravity and quantum mechanics. Later, in the 1990s, Hawking turned his attention to time travel. If wormholes allowed it, why weren't we seeing tourists from the future? His answer became known as the chronology-Pection conjecture. The laws of physics might somehow prevent time machines from forming, preserving the consistency of history. It was the universe's way of saying no paradoxes allowed. What's extraordinary is how these breakthroughs, each sparked by a mix of curiosity, mathematics, and a dash of science fiction, have reshaped our view of the cosmos. Black holes are no longer theoretical. They've been imaged, studied, and now serve as cosmic laboratories. Wormholes, though still unproven, are taken seriously enough to appear in peer-reviewed journals and Nobel Prize-level discussions. The boundary between imagination and reality has never been thinner, and it all began with a pair of physicists, nearly a century ago, scribbling equations on a chalkboard and stumbling upon a bridge through spacetime. Black holes and wormholes are connected because, mathematically, they're solutions to the same equations. The same math that predicts the existence of black holes also allows for wormholes. In fact, a wormhole could theoretically look like two black holes connected by a tunnel. But, and it's a big but, most wormholes we know of from theory would collapse too quickly for anything to travel through them. They'd be like bridges made of mist, beautiful on paper, but impossible to cross. Some scientists speculate that if we could stabilize a wormhole, maybe use something called exotic matter with negative energy, which sounds like something out of a comic book but has roots in real physics, we might be able to keep it open long enough to send information, or maybe even a person, through. That would make interstellar travel a completely different game. Trips that would normally take thousands of years could take just seconds. And since wormholes don't just connect 2 points in space, but also in time, they raise even wilder possibilities. Could you theoretically travel through time using a wormhole? The equations say yes. The practical challenge is saying not anytime soon. There's a moment in every great story where everything you thought you understood suddenly tilts, like the floor dropping beneath your feet. The same thing can happen in science. 1 minute, you're marveling at the elegant possibility of wormholes, cosmic shortcuts, bridges between stars, tunnels through space-time itself. And then someone tells you the twist: they might be completely useless. Not because they're fake or impossible in theory, but because they'd collapse the moment you try to use them. Not slowly. Not after decades of cosmic travel. Instantly. Gone in a puff of exotic smoke. Wait, what? It turns out that wormholes, those fantastical tunnels predicted by Einstein's general relativity, come with a deadly flaw built right into their cosmic DNA. They are exquisitely delicate, like soap bubbles suspended in the void. The second anything, light, particles, even a whisper of radiation, enters the throat of the wormhole, the tunnel slams shut. The universe has no patience for open doors. This bombshell came into focus when physicists started seriously analyzing wormholes in the late 20th century, especially after Kip Thorne's famous 1988 paper on traversable wormholes. The math was seductive. It showed that under just the right conditions, you could walk into a wormhole and emerge light, years away, or perhaps centuries into the future. But the devil is always in the details, and in this case, it was quantum physics, the unruly sibling of Einstein's graceful equations, that dropped the hammer. Here's the problem. Even empty space isn't truly empty. Thanks to quantum mechanics, particles and antiparticles constantly flicker into existence, then annihilate each other in an instant. These ghostly fluctuations are everywhere, always buzzing, even in a perfect vacuum. And when you apply this idea to a wormhole's throat, the narrow tunnel linking 2 points in spacetime, those quantum jitters become dangerous. They produce what's known as vacuum polarization, a buildup of virtual particles that carry energy. It's like this: imagine trying to walk through a narrow hallway made of Jell-O. The moment your body presses forward, the hallway starts to wobble and collapse. But now imagine that even your flashlight beam, the softest glow, causes the hallway to vibrate and vanish. That's what radiation does to a wormhole. A single photon, a speck of energy, is enough to destabilize the tunnel. And the kicker: even if you tried to be clever, by shielding yourself, by sending only light through, the universe still wins. Because even your own presence, your mass, your energy, is enough to snap the throat shut. This phenomenon was examined in chilling detail by physicists like Matt Visser and others, who showed that maintaining a wormhole required exotic matter, stuff with negative energy density. Not just weird matter, truly alien, universe-defying matter that doesn't exist in any known form. And not just a little of it. You'd need vast amounts perfectly arranged to hold the tunnel open, like trying to prop open a hurricane with a paperclip. Worse still, Hawking and others pointed out that wormholes, if traversable, could become time machines. If one end of the wormhole were accelerated close to the speed of light, then brought back, time would have passed differently at each mouth, a quirk of relativity known as time dilation. Now you'd have a loop go into one end in 3025, come out in 2025. The implications are staggering. Paradoxes explode like fireworks. Could you go back and prevent your own birth? Could history unravel? This theoretical time travel possibility prompted Hawking to propose the chronology protection conjecture, a kind of cosmic veto. The idea: the universe won't allow time machines. And how would it enforce this law? By unleashing quantum radiation the moment a wormhole becomes time travel capable. As soon as a timeline is threatened, the wormhole throat floods with energy and collapses under the weight of its own potential paradox. It's almost poetic, like the universe is guarding its secrets, allowing us to glimpse possibilities, but slamming the gate shut before we can misuse them. Wormholes remain a tantalizing what if, a symbol of human imagination brushing against the limits of reality. But their collapse under radiation isn't just a technical glitch. It's a message, a warning. The universe whispers, some doors must remain closed. Still, physicists continue to probe, dream, and calculate. Could exotic matter be created or discovered in quantum fields we haven't yet mastered? Could wormholes be stabilized for mere milliseconds, just long enough to peek through? Or is it all a mirage, a mathematical illusion painted across the canvas of equations with no physical counterpart? These aren't just questions for blackboards. They shape how we understand time, causality, and the structure of everything. And perhaps the greatest twist is this: the very tools we use to understand wormholes, the math, the theory, the quantum dance of particles, are the same tools that make them collapse. It's as if the act of understanding itself unravels the mystery. The map erases the road. So while the idea of a wormhole remains irresistible, the truth may be more haunting. These cosmic tunnels might really exist, and we might never, ever be able to step inside. We gaze up at the night sky not just to see stars, but to feel something old and unspoken. A sense that there's more than this world of clocks and commutes, of birth and decay. Somewhere beyond the sky's deep curtain, we imagine answers. Not just to where we are, but who we are. In that silent hunger lies the reason why black holes and wormholes aren't just equations or strange anomalies in space. They're reflections of the deepest parts of ourselves. We chase them because they represent the ultimate frontier, both out there and within. Black holes are born from death, the final breath of a collapsing star. Yet, what they leave behind isn't emptiness. It's a mystery wound tighter than anything else in nature, a point of infinite density, a place where space folds in on itself and time halts. They are the universe's punctuation marks, reminders that even the grandest of cosmic events come to an end. But wormholes, those theoretical cousins of black holes, whisper something different. They suggest that an end might also be a beginning, that folded space might not just crush and consume, but connect, that the universe might be threaded with hidden doorways, each one a shimmering question, what lies on the other side. The fact that we even consider such ideas speaks volumes about our species. Wormholes and black holes are not things we can touch, not yet. They lie beyond reach, beyond certainty. And yet, we build telescopes to chase their shadows. We design equations to describe their contours. We fill pages of science fiction with their possibilities. Why? Because deep down, we are creatures of wonder. The human brain, tucked into its fragile shell, dares to map a cosmos billions of light years across. Not because we must, but because we can't help it. Curiosity is stitched into us. There's something achingly poetic about how these cosmic phenomena mirror our own existential questions. A black hole, in many ways, is the embodiment of the unknown. A place where all laws break down, where nothing escapes. Isn't that, in some sense, what we fear in death? The silence, the vanishing. The idea that all our stories, all our love, all our dreams could collapse into oblivion unnoticed. And yet the mathematics of a black hole also hint at structure, symmetry, even beauty. They obey Einstein's field equations with ruthless precision. There is order within the chaos. Maybe that's the comfort. Maybe even our ends are woven into something larger and more elegant than we can grasp. And wormholes, those theoretical bridges between distant realms, are dreams of escape. They tempt us with the idea that we could skip over the slow grind of time and distance, that we might bend the rules and reach for something impossible, to reunite with what's lost, to see what lies ahead, to touch the future or revisit the past. Who among us hasn't longed for that? We bury our loved ones and wish for a tunnel back. We see our childhood homes in old photos and ache for a passage through time. In some quiet way, wormholes feel like the universe answering that yearning. Maybe, just maybe, it's possible. But even in their fragility, even in the likelihood that they might collapse the moment we reach for them, there's value. Because the dream matters. The questions matter. They point to something universal, our refusal to accept limits. We know that time only moves forward, that death is irreversible, that distances in space are too vast to cross in a single lifetime. And yet we ask, what if they weren't? Wormholes and black holes force us to think not just about physics, but about perspective. What does it mean to be a being that can imagine traveling across the universe or folding time like paper? What does it mean that we can create mental models of realities that may never exist simply because the logic allows them? That power, to imagine beyond the bounds of the known, is a defining trait of consciousness. The universe has given rise to something within it that can reflect upon itself. We are the universe becoming aware. We are stardust that questions the stars. And perhaps the most profound realization is that the very act of wondering is enough. Even if wormholes are forever unstable, even if black holes remain impenetrable fortresses, their presence in our imagination lights something within us. They remind us that not everything worth seeking must be found. The journey to understand, to reach, to question, these are acts of defiance against the darkness, against finality, against forgetting. In the end, wormholes and black holes may be less about travel and more about transformation, not of matter, but of meaning. They invite us to peer into the abyss and not look away, to ask the kinds of questions that stretch the mind and soften the heart. They remind us that the universe is not cold and distant, but alive with mystery, and that we, brief sparks of awareness on a pale blue dot, are part of that mystery too. Maybe that's why we keep looking up. Because every black hole is a challenge and every wormhole a promise. Because somewhere in those impossible curves of space-time is a mirror. And in it, we see not just the stars, but ourselves. There's something profound about the act of wondering. It's not just a pastime or a curiosity, it's a signal. A signal that our minds are wired to reach. To imagine, to stretch beyond the familiar edges of reality. When you stand under the night sky and feel the smallness of your body against the vastness of it all, something stirs inside you. That feeling isn't fear, it's connection. You're not just looking at the universe, you're feeling its pulse echo in your own. The atoms in your skin were forged in ancient stars, born in the furnaces of cosmic collapse. The iron in your blood, the calcium in your bones, the oxygen in your lungs. These are not native to Earth alone. They are gifts from the death of stars, scattered across space and gathered here over billions of years to make you. So when you wonder about black holes or trace the curves of a wormhole with your imagination, you are not reaching outside yourself. You are returning home to a place you've always belonged. Our questions are not accidents. They are the consequence of a universe that evolved not only galaxies and nebulae, but consciousness capable of asking what it all means. Somewhere in the silence between photons and particles, the universe whispered the ability to wonder into life. We are not just spectators in this cosmic theater. We are the scriptwriters, the audience, the actors, and the stage itself, all at once. To ask is to participate. Every great discovery begins with a question that seems impossible. What lies beyond the stars? What happens at the edge of time? Can we ever step through the fabric of space itself? These questions don't just give us science. They give us purpose. They tell us that the story is not finished, that there is always more to learn, more to feel, more to become. They remind us that ignorance is not a curse, but a canvas, that mystery is not a void, but an invitation. In a universe that measures its age in billions of years and its size in trillions of miles, it would be easy to feel insignificant. But that would be a mistake, because your thoughts, your ability to contemplate quasars and quantum foam, to imagine the impossible, to dream about what came before and what lies ahead, these things are rare. As far as we know, they may be unique. The cosmos has taken a portion of itself and turned it into a question-asking machine. That machine is you. And when we ask questions about black holes, about wormholes, about space and time and reality itself, we are not just trying to solve equations. We are trying to find our place, to understand how something so vast could make room for us, and what we are meant to do with that miracle. Perhaps there is no final answer. Perhaps the point is not to reach a destination, but to keep walking, to keep asking. The night sky is a map not of limits, but of possibilities. Every point of light is a memory of something distant and ancient, and every shadow between those stars is an invitation to discover more. We were not given a manual for the universe. We were given curiosity, and that is more powerful than certainty ever could be. You may never step through a wormhole. You may never see a black hole with your own eyes. But the fact that your mind can imagine it, that your neurons can simulate the bending of space-time, can model a reality where gravity becomes a doorway, means that you are, in some essential way, part of it all. The universe made you capable of awe. Don't ignore that gift. Because there will always be people who tell you the questions are too big or that some answers don't matter. But they do. Every time we choose to ask why or how or what if, we are choosing to light a candle in the darkness. And if enough of us keep that flame alive, we can turn mystery into knowledge, and knowledge into meaning. So look up, not in fear, but in recognition. You are not lost in this universe. You are of it. You are its eyes, its voice, its questions. And if you choose to be, its answers too. And somewhere out there, in the fabric of space-time, in the curve of a forgotten galaxy, or in the equations scribbled on a chalkboard at midnight, there is another secret waiting to be asked, another door waiting to be imagined, another piece of the cosmos waiting to remember itself. Through you.